Okay, so welcome. Happy Tuesday of week 9. We're so close to done. You guys have been doing great. I'm very impressed with the progress everyone's making. I know it's been rough, but you guys are doing fantastic. So I think that today's class is probably on the shorter side. But if I combined today and Thursday, it'd be super long. It's Thursday's like normal size length class, but today's a little bit on the shorter side. There's no actual math today. We're just going to be talking about the setup and the conclusion. We're just not going to do the middle stuff. We're going to talk about hypothesis testing. So the first thing we're going to do is we're going to learn about null and alternative hypotheses, talk about what they are, and we're going to talk about how to write the setup for those. And we're going to talk about what a type 1 and a type 2 error is and how to state the conclusion of a hypothesis test. That's all 10.1. So we will completely be done with 10.1. And so you'll be able to do that assignment. And then 10.2, we're not going to get to the math part of 10.2, but we are going to talk about the ways to conclude your hypothesis test as far as um, when you get a certain result with your math, um, how to determine how to conclude the conclusions to draw based on that. Hypothesis testing is super important. It is something that I enjoy using, and I've seen a couple of students, probably only a handful of students have used it in their final projects, but it is more common in final projects than the confidence intervals. But hypothesis testing actually can be kind of fun to use in your final project if you choose to. You don't have to, but it can be kind of fun. So, all right. So that's today, and we will jump right in with our No Math Tuesday. So a hypothesis. So a hypothesis, it's a statement that we would make about a characteristic of a population. Um, it's you'd kind of basically you're going to make a statement about what you believe, and then you will take a sample and you will start trying to prove what you believe. It's just a hypothesis. It's an educated guess. And so we're going to talk about we're not going to be using multiple population parameters. We're going to take like specific ones. Specifically, we will look at a proportion and we'll look at a mean, just like we've been doing for the past couple of weeks. So we'll have one way to do it for proportions and one way to do it for means. And yeah, it's not too bad. Don't worry. Okay. So here's some examples of our hypothesis, our claims that we will make and that we try to prove with our data and with our math. So we might say in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So this researcher isn't saying whether he thinks that more people do or fewer people do. He's just saying he thinks it's different. He doesn't think it's 62%. So this is one claim that somebody would make. There's a second one. According to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. So this person thinks that people are talking longer on the phone on average than previously. So that his claim is that they talk longer than 3.25. Our last one. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased since then. So based on this new manufacturing process, they think that it has improved the standard deviation so that things are more consistent. We are not going to be writing hypotheses regarding standard deviation. There might be some to write for 10.1 in your homework, but we aren't going to be doing math for standard deviations. We'll only be doing means and proportions, but you might have to do a setup of one with standard deviation. I can't remember. All right. So when we do these kinds of tests, because generally we can't have access to the entire population. We can't take a sample of the entire population, so we have to take these guests and we have to give samples. And basically, what we do is we will determine the probability of getting a sample um, like the one we have, given the mean or the proportion that we have. So basically, and I know this is going to come up later, but basically, what we're doing is we're taking our confidence interval. So, like if this is my confidence interval, that this is what we created in 9.2, and my sample lands out here, then I would say that this probably isn't true anymore, and this is probably true because the probability of getting this sample with this confidence interval or with this mean, the mean that's in here, it's the probability is too small. We go with the unusual. Don't worry, we go a lot more in depth, but that's basically what we're doing. We're trying to determine if the sample that we have is inside or outside the confidence interval, and we're going to draw our conclusion based on that. All right. So, hypothesis testing. We take some sample evidence and the probability, and then we're using it to test statements against information that we already have or like previous information. So, like for example, if I believe that 64% of households owned a dog, um, and I would have to test that. I would have to test my hypothesis that more than whatever the previous study is, that more than that have a dog. I would have to test that. And it's really not that difficult. I think y'all are going to do just fine. So here's our steps for hypothesis testing. The first thing you're going to do is you're going to make a statement regarding the nature of the population. Usually, this would be something like that is already out there, a study that is already out there. So it could be something like on the Mars website, it shows that 13% of all M&Ms are red. I don't know, I just made up that number, but the Mars website says 13% of all M&Ms are red. I think that there are more than 13% of M&Ms, or red M&Ms in each bag. So now I'm going to collect evidence. So now I'm going to take a sample. I'm going to get a bag of M&Ms and I'm going to take a sample and I'm going to determine, I'm going to analyze my data and I'm going to determine the probability of getting the number of M&Ms in my bag that are red, that proportion. Is it probable that I could get a proportion of M&Ms that I have in my bag, given that 13% are red? So if that probability is too small, then we would say not likely. If that probability is pretty high, then it's quite possible I could get that sample. That's kind of where we're going with this. So our null hypothesis is the test that we're stating, that we're testing. We're going to believe in the null hypothesis until we have proven different. The null hypothesis is it's the given, or so this would be the 13% of M&Ms are red on the Mars website. This would be somebody else's study that they did that says that I don't even know. I can't even make up my own thing right now. That 64% of households have a dog in them. If there was a previous study that said that, then that's what I'm banking on until I can show different. This is your statement we're trying to prove wrong. And it is this right here. Let me get rid of this. This right here, H sub 0 is pronounced H naught. Anytime you have something sub 0, it's H naught. And this is our null hypothesis is H naught. Our alternative hypothesis, it's H sub 1. Sometimes it's H sub A, but it's usually H sub 1, but I wanted to just show you that just in case I accidentally write it that way. This is the alternative hypothesis. This is the statement we're trying to find evidence to support. So this would be me saying that I believe that the number of red M&Ms is the percent of red M&Ms is greater than that 13%. That would be my alternative hypothesis. That's what I'm trying to find evidence to support. I'm trying to show that more than 13% of the bag of M&Ms is going to be red and that they're wrong. Their information is wrong. This is our alternative hypothesis. We're trying to support this. Okay. So this is an important sheet. This is an important page. If you tab your pages, this is important. So there's three ways we can set up a null hypothesis. Now, or a hypothesis test. The null hypothesis will always have an equal sign. Notice it's always equal. The null hypothesis always has an equal sign. If it's a two-tailed test, you'll see the words different. So if I say that the researchers think that it's different, if the words different are there, it is a two-tailed test. And you're going to put with your alternative hypothesis, you're going to have a not equal symbol in there. So two-tailed tests would have not equals. So that means it could be higher or it could be lower, but it's just different. I just think it's not that. It's just different. A left-tailed test would be less than, smaller than, be smaller. I don't know, any other words meaning smaller. You're going to the left. So it's a less than symbol. So my null hypothesis will still say be equal, but my alternative hypothesis will stay less than. And the right-tailed test is greater than or more. So if it's more, higher, greater than, any word meaning bigger, then it is a right-tailed test, and you're going to use the greater than symbol. Once again, null hypothesis is always equal. Always equal. Any questions so far? I'm going to give some examples. You need a second, Hannah? Okay, no problem. This is why it's good to occasionally have your screen on. I could see she was still writing.
Okay, we're good. Sorry, thank you.
Oh, I don't have sound. Go ahead.
We're good. Thank you.
All right. In other words, the null hypothesis is the status quo. No difference. It always has equality. So we assume the null hypothesis is true until we have evidence to the contrary. Okay, we're trying to find evidence to support the alternative hypothesis. You're trying to find that evidence. Kate, I understand how that is. Man, I had my grandkids last night and they were here pretty late, so I still haven't cleaned up after them. So my house is currently destroyed. My Monday night, my daughter goes, has exercise classes after work. She goes and works out. So I watch two of my grandkids and they're whirling dervishes, but they're amazing. Okay, let's move on. Okay, so let's talk about what the null and the alternative hypotheses are. And let's talk about two-tailed, left-tailed, or right-tailed. And the next screen will give you the answers, but we're going to work through them together and I'm going to write them here because it's what I do. So 2008, 62% of American adults regularly volunteered in their time for charity work. A researcher believes that percent is different today. You see the word different. This is a two-tailed test. Yes, good. Good job. Okay. So our null hypothesis, our H naught, will look like this. Let's see here. Our P is equal to 0.62. So the proportion of people who volunteer is equal to 6.62. We believe this is true until we have evidence to support something different. Our alternative hypothesis is going to be P is not equal to 0.62. These two numbers are always the same. The only things that change are null to alternative and your symbol. Those are the only things that change are the symbol and the null hypothesis and the alternative hypothesis. Those are the only things that change. Okay, I'm going to show you what this is going to look like when we do our math. So this is a two-tailed test. So here we go. This is now I don't have my alpha yet. So we're going to be using alpha again. I don't have that yet. So I'm just going to give a rough drawing. So my proportion might, whoa, I didn't mean to do that. My 62% is right here. And I created a confidence interval. So my confidence interval is this space right here. So if once I do my research, if I'm outside the confidence interval, either here or here, I could state that my alternative that I have evidence to support my alternative hypothesis. So if my evidence lands outside that confidence interval, then I can state that I have evidence to support that null hypothesis or that alternative hypothesis. That's what's happening with this one. Definitely going to get into more and all the math around it and everything. I'm just trying to give you a visual. Okay. So this is all the stuff that I just said. So 62 null hypothesis, is right here. Alternative hypothesis, it's a two-tailed test. And there we go. This is all the stuff I just said, but it's nice for the slides to have it printed out. So there we go. Okay, let's do the next one.
Hold on. Did you say that if it's outside of there, then there is evidence to support it, but if it's equal to, then there's not evidence?
Okay, so we are trying to support this right here. I'm trying to support the alternative hypothesis. So if it lands out here, if it lands outside my confidence interval, then there's evidence to support the alternative hypothesis. There's evidence support that it's different today.
Okay.
Yeah,
Thank you.
you're welcome. Good question. Okay, so let's do this one now. According to a study published in March 2006, the mean length of a phone call was 3.25 minutes. Researcher believes that mean length of a call has increased since then. Has increased. Sounds like greater than to me. This is a right-tailed test. So what this is going to look like, my null hypothesis is that the mean equals 3.25 minutes. My alternative hypothesis, the mean is greater than 3.25 minutes. So it's a little bit different here with because our confidence intervals were always two-sided, but because our null hypothesis, we can have a right-tailed or a left-tailed. Sometimes they're one-sided. So what this would look like, let me draw my curve. My confidence interval basically is all of this stuff over here. So my mean, that's really ugly mean. My mean is in the middle. This would be my 3.25 minutes. So if my sample, when I choose my sample, if it lands me out here, then I have evidence to support the alternative hypothesis. If it lands in here, I don't have that evidence. I don't have sufficient evidence to support the alternative. So this right here would say our H1 is true. And then in here, we would, our HO is true. Now, these aren't the words we're going to use, but I'm just trying to give you an idea of what we're doing here. So outside, so if I'm off to the right, outside that confidence interval, then I would have evidence to support that alternative hypothesis. Questions so far? We doing okay? Okay. So here's all the stuff that I just said. Let's move on. The last one. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With the new equipment, the quality control manager believes the standard deviation has decreased. Sounds like less than to me. Therefore, this is a left-tailed test. The picture of the curve doesn't work as well with standard deviation. We don't do any math with the standard deviation, so I'm not going to draw it here, but I am going to write the two hypotheses. My null hypothesis, sigma equals 0.23 ounces. Or alternative hypothesis, sigma is less than 0.23 ounces. So once again, we're looking for evidence to support that alternative hypothesis. What's really cool is that the math here isn't going to be super new. We're just kind of, I mean, we're kind of applying it in a different way. So, I mean, it's going to be, we're just kind of tweaking what we already know a little bit, which hopefully that doesn't mess you up too much. But I can tell you, I teach it different now than I teach it on the pre-recorded videos. So if you watch the and Adrian, I think you watch those videos, don't you?
Yes, I do. It always helps when I watch these as well.
Yeah. Well, I teach it different now than I did back in 2020. I had like an aha moment somewhere in the middle of all of there, on how to teach it differently. But
This is really helping. Thank you.
you're welcome. But I bet that's probably good though. It's almost like two different people. It's 2020 me and 2025 me. We're two different people. We've grown since then. All right. Okay, so this is all the stuff that I just said. Left-tailed test, our alternative hypothesis, it's less than. Just, I know I keep saying it. The reason I keep reminding you that the null hypothesis is always equal is because inevitably I have 4 or 5 students every term that starts putting less than and greater than and all of that in there. So that's why I say it, that it always has to be equal, always equal. And then this is where you're going to have the not equal. None of this is going to be equal. Our alternative hypothesis is always either going to be not equal to, less than, or greater than. Okay. Here's the different outcomes that we can have. Now, these are the errors. Now, I frequently forget the errors here. And so make sure that you have your notes for this part. I believe that your the quiz for this week has a question about, I think it's the type 2 error. I can't remember. And there is a question on the test that asks you to state the type 1 or type 2 error in the context of the problem. This can be kind of confusing. I grade super lenient on these. I'm pretty lenient with how I grade. If you sound even like vaguely intelligent on the matter, you will get full credit. So I'm not looking for rocket science. Okay, so number 1, these are good outcomes. 1 and 2 are the good outcomes. If you reject the null hypothesis when the alternative hypothesis is true, this is the correct decision. So if we find the evidence to support our alternative hypothesis, we will reject the null hypothesis. We will say the null hypothesis is not true. I have evidence to support it isn't true. So therefore, I reject the null hypothesis. I don't like the word do not reject. We generally say fail to reject. I would, when you are answering in the on the test, and if you're typing it out in the homework, make it very clear whether you are rejecting or failing to reject the null hypothesis. You may state there's sufficient evidence to show that the alternative hypothesis is true. That's fantastic, but I want you to state that the null hypothesis is rejected or failed to reject. So please be very clear on whether or not you're rejecting the null hypothesis. Okay. There's my PSA. Okay. So the second good one is if we don't have evidence to show that the alternative hypothesis is true, then we will fail to reject the null hypothesis. So now we're going to have 3 and 4 are the wrong answers. They are the errors. It's a type 1 error if you reject the null hypothesis, but the null hypothesis is true. So if you don't have evidence to support your alternative hypothesis, but you still reject the null hypothesis, that's a type 1 error.
When would you not have evidence?
So if, let's say I have I'm going to make a two-tailed test just because it's easy. So let's say this is my confidence interval, and I did all my math, which guys are gonna learn on Thursday. I did all my math, and my sample landed. My sample landed in here. If my sample landed inside the confidence interval, then I don't have evidence to support the alternative hypothesis. But if I reject the null hypothesis at this point, that's a type 1 error. Does that make sense?
Thank you.
You're welcome.
Yep.
Good. Okay. Let me erase that. So now the opposite. If if I have evidence to support the alternative hypothesis, but I don't reject the null hypothesis, that's a type 2 error. So it's the opposite. So once again, let me draw my picture because why not? So this is the safe area in there. Or this is actually called out here. This is called a critical region, just so you know, it's okay. But if I have, let me see here, let's say that I landed out here. My sample landed me right out there, but then I failed to reject the null hypothesis. This is a type 2 error. Okay. Now, as I said, if you sound mildly intelligent, even mildly intelligent while you're doing these, you'll get full credit on it. I have
Can you
great.
state-
Go ahead.
Sorry. Can you state what the outside area was called again?
Critical region?
Okay.
Yeah. Yeah, so that would be yes, critical region. There we go. The other one's probably safe region, but I don't think we've ever called it that, so don't call it that. Maybe I just made that up. I like it. I might use it. But that's a critical region because that's the area I can't land out here and still have a null hypothesis be true. Right, so there's type 1 and type 2 errors. I am going to talk about the probability of making these errors. Oh, these are so rough. Okay, I'll talk about that in a minute. These are rough, and I'm going to let the slides do these because these are really rough, but you're going to need to do this on the test. Once again, sound mildly intelligent. You got this. So we want to do a type 1 and a type 2 error on the 62% of American adults regularly volunteer their time for charity work. A researcher believes that the percent is different today. This is why they're tough. Type 1 error. If the researcher concludes that the that P doesn't equal 62%, so if it falls outside of that area, but the true proportion of Americans that do charity work is 62%, then that's a type 1 error. So if they say that if the evidence supports the alternative hypothesis of a different amount of people volunteer, but they fail to reject. I just did it backwards, didn't I? Just did it backwards. See, I told you. I'm terrible at this. If the researcher concludes, so if the researcher rejected the null hypothesis, I did it backwards. If they said, hey, it's different, it's not 62%, but then it turns out to be 62%, that's a type 1 error. Type 2 error, if the number of people who volunteer for charity work is different than 62%, but they're saying, hey, it's only 62%, that's a type 2 error. Really, just use your notes.
So do the error, so do the, okay, so if we say like the H, what did you call it? H naught,
Uh-huh.
we is the probability of, let's say, 62, and
Uh-huh.
then they, their alternative is that it's not equal to 62. Are you saying that like in the type 1 and type 2, their final conclusion, like they lied about it? Like they're
Yeah.
not claiming that that it was, that their hypothesis, I don't know, like how am
It's
I
usually not a lie. It's usually just they made a mistake.
made him, okay.
That's why they say it's an error rather than saying, hey, they're making stuff up. It's usually a mistake. And it's usually it lands on the line like it's really close.
Okay.
They'll make an error. So basically the researcher is saying, hey, look, I have evidence to show that it's not 62%, so I'm going to reject the null hypothesis. Yet it actually is 62%. That's the type 1 error.
Okay.
On the other hand, um, he says, oh, look, I don't have any evidence to show that it's not 62%. I'm not going to reject the null hypothesis because my evidence isn't conclusive that it's not 62%. Yet it turns out that maybe it was 68%. So it's usually an error and they're not like,
Okay.
yeah, it's usually not somebody lying. However, I'm sure it happens. Okay. Yeah, we just did, okay, we're gonna do the other ones now. Did we already do these? So this is for the cell phone company. So the researcher believes the mean length of the call has increased. We're gonna jump over here. So type 1 error is saying that the researcher says that they have evidence to show that the mean is greater than 3.25%. However, the average length of a call is only 3.25%, then that's a type 1 error. Type 2 error would be I'm going to say that I don't have sufficient evidence to show that a cell phone call is greater than 3.25 minutes, but it is actually longer than 3.25 minutes. Then that's a type 2 error. So you'll probably have some scenario and you're going to do some math on the scenario. And I'm going to say, in the context of this problem, what would be a type 1 error or what would be a type 2 error? And you're just going to give me some words that are, they believe that it was, yet it wasn't, or they believe that it wasn't, but it was. So you're just going to write out like that. So if you have your slides on you, you probably could just type almost exactly this type of thing, but change the story. And I'm not going to be mad at all. But this is a standard I have to test on. There's, sometimes I would love it if I had more control over what I thought was important, but some things, it just is what it is. We don't have as much power as we think we do. Okay. You definitely have this on your quiz. So the probability of getting a type 1 error is alpha. The probability of getting a type 2 error is beta. This is just the probability of that. That alpha that we use, that we're going to be using for our, we used alpha already for our confidence intervals. That's basically the probability of getting a type 1 error. And as my alpha gets bigger, as my probability of type 1 error gets bigger, my probability of a type 2 error gets smaller, and vice versa. So you are going to have a question on your quiz that says, what is the probability of getting a type 2 error? If you just say beta, you are good to go. Don't make it more complicated than it is. Get me giving you all the quiz answers.
Thank you.
You're welcome. Adrian, I hope you didn't already take that quiz. I know how you are.
I did not yet because I learned my lesson.
Good job. All right, moving on. I just said this, but okay, our alpha, our probability of making a type 1 error is called the level of significance, and we're going to be using this a lot. Our level of significance is alpha. We've already been using alpha a little bit. It basically is the same thing. We're just giving it a different name. This is the probability of making a type 1 error. But we're going to be using that. Now, you are generally the researcher chooses the alpha. However, you will always be given your alpha. You don't have to make choices about what your alpha is unless if you use hypothesis testing for your final project, you will choose an alpha. Just choose 0.05. 0.05 is a good alpha, and we're used to using 0.05 for something being unusual. So if you're going to end up using hypothesis testing in your final project, just use 0.05. It's just easy. All right. Are we okay so far? I haven't lost anyone yet. I know it's a lot of information.
Can you define what alpha has meant in the last couple lessons?
We used alpha for the tails of the tails outside of our confidence interval. So if we had, this was my confidence interval, each tail was alpha divided by 2 because it was cut in half. So each of our tails was alpha divided by 2.
So
And
it kind of was like the area, just the area outside the confidence.
right, exactly. And it is because remember how the area corresponds with proportions and probability. It's still the same thing here. So if my probability lands out here, then we can reject the null hypothesis. Then we have evidence to show the null hypothesis is not true if our sample lands in that alpha area. Hopefully it'll make more sense as we go. All right. Okay, let's move on. In other words, I already said this, as the probability of a type 1 error increases, the probability of a type 2 error decreases and vice versa. I don't think that you're even asked that, but it is a thing. The most important thing to remember on the probabilities is just the probability of a type 2 error is beta. So don't go getting all crazy about that. That's as simple. If you just type in your little thing, type the probability is beta, you're good. Okay. This is important. We never accept the null hypothesis. You don't have access to the entire population. We don't know the exact value of that parameter. We can never know the exact, so we don't accept it. We either reject it or we fail to reject it. So reject, reject or fail to reject. There is no accept. There we go. So we never say somebody's innocent when they go to court, when they have a defendant, they're not guilty or they're guilty, because not guilty does not necessarily mean innocent. It just means they found not guilty. So reject or fail to reject, there is no accept. Do not use the word accept. We're almost at 10.2, but we're not, we're just dipping our toe into 10.2. Okay. Okay, so we're going to talk about what conclusions look like. Now, my conclusions do not have nearly as many words as the textbook conclusions, and I am the one giving you a grade in the end. So, you do with that what you will. I will accept if you want to use a novel like the textbook does, go for it. So we are using the cell phone one where cell calls are 3.25 minutes. We believe that the length of the call has increased. So the sample evidence indicates that the null hypothesis should be rejected. So we are going to be rejecting the null hypothesis. Here's words. The statement in the alternative hypothesis is that the mean length of a call is greater than 3.25 minutes. Since the null hypothesis is rejected, there is sufficient evidence to conclude that the mean length of a call on a cell phone is greater than 3.25 minutes. That's a lot of words. This is how I would write it. There is sufficient evidence to show that the mean length of a call, my handwriting's really bad, sorry, is greater than 3.25 minutes. Therefore, we reject the null hypothesis. This is how I write it. Those are my words. Man, reject. I lost part of my E. Now, I don't, as long as you have to state somehow you have to state that you have evidence to show the alternative hypothesis, and you have to use the words we reject the null hypothesis. Now, when you are taking the test, and I probably will say this again later once we're doing the math and everything, when you are taking the test, I would like you to tell me what the evidence is. And we're going to talk about what kind of evidence shows that. But I want you to tell me what the evidence is. When we're doing the math on Thursday, I will try to be clear in my conclusion so that you can state a really good conclusion that's going to make sure you get all the points. Because this right here doesn't tell you how you know, but that's mostly because we haven't done the math yet. This doesn't tell which evidence you used. This doesn't say that. Because on the test you're trying to show me that you understand the material, I want you to be able to tell me this is the evidence that I have. Here's what I have. So you're going to be kind of presenting your case a little bit. And actually the nice thing is when you're telling me what that evidence is, it's going to be even fewer words than this, because you'll be able to just say, because of this evidence, I reject the null hypothesis. It's perfect. It'll be beautiful. Okay, let's move on. Okay, so now the sample evidence indicates that the null hypothesis should not be rejected. So now we're going to state that conclusion. Here's what they say. Since the null hypothesis is not rejected, there is insufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25%. In other words, the sample evidence is consistent with the mean length of call equaling 3.25 minutes. Here's the way that I would write it. We do not have sufficient evidence to show that the mean length of a phone call is greater than 3.25% or 3.25 minutes, sorry. Therefore, we fail to reject the null hypothesis. Bam. All right, any question on the conclusion so far? Now, you don't have to be fancy though, as long as you get the information across to me. I'm not looking for flowery words. It is absolutely okay. This isn't an English class. Doesn't need to be super flowery. You just need to tell me that there's not evidence there and you fail to reject or whatever. Just as long as you get your point across and tell me what evidence we're looking at, you're good. I don't care if your words are flowery. They don't have to be beautiful. I'm not looking for poetry. However, it would be really cool to get a conclusion in poetry. That would be kind of fun. So, I mean, if you're so inclined, go for it. I would probably save it. I'd probably print it off and save it. Okay. Can I move on? We good? Okay. We're at 10.2 if you keep track of those things. You have enough information to finish your 10.1 homework. So we're doing 10.2. We're not going too deep into it. This is all I'm going to be doing is I'm going to be explaining how we determine without doing the math. We're going to talk about how we come to our conclusion so this is the end part, how we decide, how we check. Okay. So a researcher obtained a random sample of 1,000 people and found that 534 were in favor of banning cell phone use while driving. So what we want to know is it possible that the true proportion of registered voters who are in favor is less than 50%? And did we just happen to get a survey that the majority favored the policy? Or is it statistically significant? Is this number far enough away from 50% that we could say that it's definitely not 50%? That's what we're trying to figure out. Is 53.4% too far away from 50% for it to be, for 50% to be true? That's what we're looking for. So if something is if something is unlikely, if it's unlikely under our null hypothesis assumption to be true, then we say it is statistically significant. Now, I don't really care if you use that word. I kind of like it, but it's hard to say it. So, but if we find the results are statistically significant or highly unusual, unlikely, etc., then it is statistically significant and we reject the null hypothesis. So you remember a long, long time ago in the land of a couple of chapters ago, when we determined that if something happened less than 5% of the time, it was unusual. We are going to be doing that again, but that 5% is kind of a moving target. Instead of 5%, we are going to be using whatever our alpha is. I think there was one question about, I don't remember if it was women. I think it was women being hired where we moved that bar. Remember when we said we're not going to use 5% this time? We're going to use a smaller number. I think we used 2% or something. That's basically what happens with alpha. Kind of like depending on how important this thing is, we move our alpha. We'll change our alpha depending on how important it is. So sometimes I'm going to use an alpha of 2%, or I'm going to use an alpha of 1%, or you might just use the 5, or maybe you'll be like, you know what, it's not even that important. We're going to use, or we're going to use 10%. So sometimes, depending on the importance of something, alpha is a moving target. So they will tell you what significance level you're going to use. They're going to tell you what percent to compare it to. And that's basically our alpha. Okay, so what I did was I took the sample proportion and I found the standard deviation. So what I did was I found the new standard deviation depending on our sample size. So our sample size was 1,000. Well, first thing, NP times 1 minus P was greater than or equal to 10. Doesn't go away. Our sample size is definitely smaller than the population of like the US. My mean is going to be this. And this is my standard deviation, my new standard deviation. So what I'm going to do is I'm going to find the probability of getting the sample that we got if this is the mean. That's what I'm doing. So this right here is the distribution, the sampling distribution of my sample proportion. So take a look here. This is my confidence interval happening right here. It's not, though, that's only 1 standard deviation away. That's not 2 standard deviations away. But if I use 2 standard deviations, let's just do that. Let's use 2 standard deviations. So if I use 2 standard deviations away, because I have that number right there, if I took 2 standard deviations away, or I found the z-score of this 53.4%, that z-score is greater than 2 standard deviations away. Therefore, because it is more than 2 standard deviations away, it is statistically significant, and I'm going to reject the null hypothesis. We will not always use 2 standard deviations. As I said, that's a moving target, depending on how important things are. You will know what that value is every single time we do this. You're going to be given that. I might decide to make it 3 standard deviations away. But if it had a z-score of greater than 3 standard deviations of greater than 3, then I would reject the null hypothesis. But this one, we just use 2. So because 53.4% is more than 2 standard deviations away from 50%, we reject the null hypothesis. So once again, let me go back here. So this was 1 standard deviation. So 2 standard deviations is here. So this is my confidence interval in here. 53.4% landed right out here. This was my 0.534. Because it landed out there, it is outside of that confidence interval, we can reject the null hypothesis. Okay, that's the classical approach. So the classical approach, what it does is it compares the edge of your confidence interval with the z-score of your sample. If your sample has a z-score further out than the edge of your confidence interval, we reject the null hypothesis. So remember critical values? Remember those long time ago in the land of last unit, where we use those critical values, those z-scores, to find the edges of our confidence interval? Those are the z-scores we compare this z-score with. It's going to be much easier when we're actually doing math with it, but this, I'm just kind of giving you an overview. Okay.
I think I wrote things backwards in 10.1. So the reject means that I use it in my terms. I know that it doesn't mean we're accepting it or it's true, but so reject means that null is right, like nothing's changed.
No, we reject the null hypothesis if the null hypothesis is not true.
Is
So
not.
when we have evidence against the null hypothesis, we reject it.
Okay, I did write this backwards. I wrote the other way around. Okay, sorry, thank you.
Oh, you're good.
And on this slide, I was taking notes and I missed that what's the 2.5 is a Z-score?
This 2.15 right here.
Yeah,
Yes.
2.15.
This is the Z-score of, because see, let me get rid of all my marks because, I just tend to color. So this right here is the new standard deviation. Uh-oh.
Okay.
That's the new standard deviation. You kind of recognize that when you look at it?
Totally.
I got that sarcasm.
No, I kind of do. Maybe I kind of do.
So remember calculating a Z-score. I'm going to go old school here. Remember it was X minus mean divided by the standard deviation long, long time ago. I mean, this was way, way back in the beginning, back before you guys would correct my math. Okay, so this is basically the same thing. This is just my p hat, which is my sample, minus my original proportion that we had, that they gave us, this right here is my null. That's my null. And this is my sample. So you take the sample proportion minus the null hypothesis proportion, divide it by the standard deviation, the new one, and I get a Z-score. So it's the same math, it's just with our new stuff. So I found a Z-score. This is the Z-score of my sample. This is the evidence that I'm going to use to try to disprove the null hypothesis. So then we take that back and we go, okay, so now here's my setup. Here's my confidence interval. This Z-score right here on the edge of my confidence interval is 2. And that would be our critical value. You guys remember those critical values? These critical values are the edges of your confidence interval. So my critical value there was 2. That critical value at the edge of my confidence interval was 2. This 0.534, this has a Z-score of 2.15. So it's outside the confidence interval. Therefore, it's in that critical region, and I reject the null hypothesis because it didn't land in this area. Does that kind of make sense? Okay. Even if it doesn't, we're going to get there. We're going to do some math.
What is that 0.5 from? Sorry, it says standard deviations above the hypothesis. So you wrote mean probability above it?
This was the means, so remember when in 8.2 when we talked about our mean sub p equals the proportion. So when they give us a population proportion, we call that our mean.
Okay.
Okay. And in our story back here, in our story, where is it? We are saying that we think 50% of the people favor banning cell phones. That's my null hypothesis. This is H naught right here, the 50% of the people. We use H naught, that proportion, for our new standard deviation, which is what I did right there. We use the population proportion, what we're believing is true until we prove it's not. We use that for our new standard deviation.
Okay, and it'll usually say proportion with it if it gives you that.
Yeah, it'll say proportion, like right back here, it says, is it possible that the proportion is less than 0.5? So we used different here, but
No, that's perfect. Thank you.
Yep. Okay. And I'm like going way above way above what I get excited. I'm giving you extra information. I hope I'm not overwhelming your brain. Nobody go cry. We're going to dig deeper on Thursday. Nobody go cry. Just if it's a lot of information, just kind of step back and say, okay, she's going to re-explain this later. It's going to be okay. Okay. So now I'm going to take the probability. So just to kind of show you, what I did was I found the probability, of the getting a to the right of 2. So remember this z-score right here on the edge of my confidence interval. This is 2. The probability of getting too late. I'm sorry, Kate. Sorry. Okay. Probability of greater than 2 is 0.0228. So that area, the area under this curve right here is 0.0228. I know that there's 5, remember there's 5%, approximately 5% outside 2 standard deviations. 0.0228 plus 0.0228 is really close to 5%. Remember, that was just an estimate. So looking at that, because this right here, wait, hold on here. So only 2.28% is going to be more than 50.0532, which is 2 standard deviations away. So that's why we can reject our null hypothesis. This is more complicated. I'm going to go past it. I'm going to give you the other approach. So the other approach is, I thought I already gave you the classical approach we just did is if the sample proportion is too many standard deviations away, we reject the null hypothesis. This is the one that we just did. That's the classical approach. If we're too many standard deviations away, we reject the null hypothesis. We have another approach, the p-value approach. Okay. A p-value is just a probability. I don't want anyone to be like, oh no, a new term. We're just too lazy to say probability. A p-value is just a probability. So what we do with the p-value is we determine the probability of getting a sample with 0.534 or higher, and then we compare that to our alpha. So let me show you.
That number is always the same. That's random.
What number?
0.534.
This is what we just, we're in the same,
Oh,
same problem, same problem.
okay. I was okay, so it can be any number.
You're like, what the heck? Yeah. So I'm just going to jump over here. So what I did was they convert it to a z-score, but it didn't even really matter. So the probability of getting a z-score greater than 2.15 is this right here. Okay. So that's my p-value. So my p-value, I compare that to whatever my alpha is. Whatever alpha was given to you, we will give you an alpha and you compare that to your alpha. If your p-value is less than your alpha, we reject the null hypothesis. This is my high schoolers. Love this. This is the statement that's going to stick with you. If the p is low, reject the hoe. There you go.
That's hilarious.
That's what's going to get you to remember it. If the p is low, reject the hoe. There you go. So that's what we do. If the p-value is less than alpha, we reject the null. If the p-value is greater than alpha, we fail to reject the null hypothesis. Now, your homework is going to tell you which one it wants you to find. The homework will say which one it wants you to find. When we
The
take,
homework was all P.
it was all P, really?
Yep.
But didn't it ask for test statistic anywhere?
Yes, I mean, but it wants you to find the p-value for every single one. Like you can't use the classical approach.
Oh, geez, that's rude.
Yeah.
So on the test, I let you use whatever method you want as long as you show your work. You can use whatever method you want on the test because I want you to use what you're comfortable with. So on the test, if you like the classical approach better, use that. If you like the p-value approach better, use that. So whichever one you do, I usually go with p-value, but it doesn't even matter. Sometimes if I'm feeling a little sassy, I'll go with the classical approach, but either one is fine for me. Now, the homework, you got to do what they tell you, and we just kind of go along with what they do. But on the test, I don't care. Okay.
Is that rule of thumb about the p-value being lower than H naught? Is that regardless of if you're looking for right-tailed or left-tailed?
Mm-hmm. Yeah. Because the probabilities are always positive. And so, yeah, it's going to be regardless. So no matter what, if the p-value is less than the alpha, then you reject the null hypothesis. This is set in stone.
You might have said this.
Oh.
Where did the 0.158 come from? Did you minus
No,
thing?
this is the probability. I did the probability that I got a z-score of greater than 2.15.
Oh, okay.
Yeah, that's fine. We are in week 9. We are all tired. It's that you guys have had so much information put in your brains this term. I feel like
Don't you have to use the norm CDF to find that 0.0158?
you don't have to know. We have calculator functions that'll get it for you. You can. You can use normal CDF on the proportions, but you don't have to. We have calculator functions that I'm going to teach you on Thursday.
Okay.
I I was just gonna ask, are both of these methods done using calculator functions, the
Yes.
class? Okay.
Yes. Well, the yeah, actually, yeah, pretty much, yeah. Yes. So I'm gonna give you all of that, the calculator functions on Thursday. And Courtney, you will get an alpha. They will give you an alpha. They'll call it a significance level, but that's the alpha. So you don't have to worry about it. Yes. So don't worry, you'll get an alpha every time. But if you were deciding to use hypothesis testing in your final project, just use 0.05 for alpha because that's kind of been our rule of thumb. Like it's unusual if it's less than 5%. So just stick with 0.05 for alpha if you're using it in your final project. Okay, I think that was my last one. And then this is just it right here. Um, if the probability of getting a sample proportion as extreme or more extreme, then the one obtained is small. So basically, if the P is low, reject the hoe. There we go. I just can't think of a way that's going to stick in your brain better than me saying that. And that's why I perpetuate this. I keep it going because you're not going to forget that. All right, that is the last slide that I have. Any more there was really no math today. All of the math is going to be Thursday, and you guys are going to be just fine. Any questions for while we're recording?
I actually do have a question. I mean, I guess it doesn't matter that it's recording, but I was noticing on the final project information under the schedule. It's like the final project handout. It says the dates are like Tuesday, February 11th, Thursday, February 25th, and then Tuesday, March 16th, except the 16th is a Sunday.
Did I really do that? Oh my gosh. Okay.
So I just wanted to double check that.
Because the content, it says it's due on the 18th on the content, but then on the paper it shows the 16th. So I don't.
So I typoed is what you're saying?
Yeah.
Okay. So yes, I typoed. It's the 18th. So Tuesday on the 18th, you need to turn in the written report and your presentation. The presentation, there's just going to be there will be a forum. I should probably create that soon. There's just going to be a new forum created and you just post it directly in the forum.
You made it.
I haven't made the form yet. I will.
Oh, it shows.
It shows? Yeah, it probably doesn't go anywhere. Let me check that real quick. I probably accidentally did something. Why aren't you scrolling down? It probably doesn't go anywhere. So we have that. Let me see here. Oh, it does. How in the heck did I do that? I didn't even notice I did that. I guess I did. Okay. Anyway, so it's there. So the project submission, that's the presentation. So this forum that says final project submission, that's the presentation. So that's the pretty thing for everybody else, for all your classmates. That is due on the 18th, and your paper that's just for me is due on the 18th. I can't shut the forum down to not allow presentation submissions after the 18th and still allow you to comment. So unfortunately, if somebody submits a presentation after the 18th, it's just not going to get graded because I can't accept final projects late. So it's just not going to get graded. But anyway, you guys are all going to turn it in on time anyway, and they're going to be beautiful and fun. Your presentation, I'm glad that you asked this on, this isn't what you asked, but I'm glad that you brought it up. Your presentation doesn't have to show as much nitty-gritty as your paper. The presentation is the pretty that you're presenting to your audience, so you don't have to show how you got the standard deviation or tell how you calculated the mean. You don't have to show your calculations on the presentation part because all your classmates know the same math you do. Just that's where you're going to show them the pretty of this is what I found out. I compared these means. I compared this. Here's my pretty graph. Here's my conclusion. So it's the pretty. So if you were standing up in front of the class presenting, which is what we do in person, if you were standing up in class presenting, this is the slideshow that you would use to present that. It's just going to have a few more words than it would if you were in person because you obviously can't read it to them. The paper is where you're going to really get into the nitty gritty because I want everything. Now, the paper can be a stream of consciousness paper. What I mean by that is you can say, here's the question I want to answer. As soon as I came up with that question, I immediately thought, I'm going to collect data from the census.gov website. And once I collected that data, I had this idea. So I did this type of analysis. And here's what I found there. And so that gave me the idea to do this. And you can do it like that. This isn't an English class, so I'm not going to, as long as it's readable, I'm not going to get picky about it being perfect and beautiful unless you're a perfectionist. I know some of you are. I've seen it, but it doesn't have to be super beautifully written and all of that. I just need to see what kind of analysis you did. Why did you choose that? What was it? What did it show you? You have to have one hand calculated formula. Do not hand calculate the correlation coefficient. You will be really mad at yourself. Do a z-score. Can calculate the mean, something like that. So make it something simple, but part of the standards that I have to grade you on is you have to do one hand calculated formula. Just do something simple, super simple. Keep it simple. Z-scores are perfect.
Other than that one formula that we showed, are you wanting us to show math in the paper or
Yeah.
like write out the formulas?
Just the one hand calculated formula is all the math you have to really show. And my assumption is you're going to use Excel for some of it. And if you use Excel for it, you're going to attach the Excel also so that you're doing the math there. But you can say, I went to my calculator and used the one variable statistics function to find the standard deviation, which is. So just kind of tell me how you got it.
Okay, my Excel that it's just got things everywhere. I mean, there's graphs and there's charts and okay, so it's
That's okay. The Excel can be like showing your work.
okay.
And you are more than welcome to in your paper say, see bar graph titled this in Excel. You don't have to like paste it into the paper.
Okay.
Put, say I decided to do a bar graph, parentheses, see bar graph, whatever in Excel, and then tell me what the bar graph said. The other option, you are more than welcome to paste the graphs directly into your paper. Some people do that. They like that better. Either way,
Okay.
I don't care.
Are we still able to use Google Sheets or do we have to use Excel?
Um, Technically, yeah, you can use Google Sheets. I just personally hate Google Sheets, but I'm not going to mark you down for using Google Sheets. So
Okay, thank you. My computer just works better with that since I have a Chromebook.
I, oh yeah, the Chromebooks don't like Excel.
No, I have like a dinosaur computer that's like 8 years old that I have to use when I use Excel. So Google Sheets is nicer for me.
Yeah, I'm just not a fan because it doesn't have I learned on Excel and Google Sheets doesn't have the functionality that Excel does. But if you want to use Google, I'm okay with that. I'm even okay. I have a MacBook. That's what I'm on right now with y'all. I'm okay if somebody really likes numbers, which I don't know why anybody in their right mind would like numbers. But you took this class, so you're probably not in your right mind anyway. So
Okay, thank you.
you're welcome. All right. Anybody else while we're still being recorded?
Is it okay to use, oh, sorry.
No.
I just saw Courtney's message.
Yes, Courtney, you can make it in any program. You can use Prezi, you can use PowerPoint, you can use Google Slides, you can use I think Apple has something also, but whatever you want to use it in is fine. Okay.
Is it listed on the handout sheet for that? You said there's two ways to get extra credit by sourcing other chapters. Are those chapters listed?
It's just anything after chapter 10.
Oh, okay.
So if you have the textbook, after chapter 10, I think I might say chapter 11, I don't know. Chapter 11 compares there's a little bit different math, so you're gonna kind of have to learn a little bit of new math if you go to chapter 11 if you want the extra credit. Um, but it's not super complicated. And there's other things. So if you take any others, so if you're going to use other statistical methods that are beyond chapter 11, and you want to know, hey, will that suffice for the extra credit? Send me a message and just kind of tell me what it is you're thinking of using, and I will take a look and I will let you know if that will work. I've only had two projects ever get extra credit in my class, but it's mostly because nobody really tries.
I looked at that and then it said comparing means. So what I did on my slide was I have three data values. So I had like means of the current ages of the people I surveyed and then means of the age they were when they moved out. And so I just like subtracted the current age means from the means they were when they moved out, like and compared that to the associates and then to the masters and the bachelors. Would that count as comparing the means? Because I went on like a math tutor and tried to talk about that, and she said that's what it was. So I just wanted to make sure that that would count by you.
Take a look at chapter 11. Just flip through that. Because what you're saying kind of sounds right, but it's hard for me to picture it with what you said. Go ahead and flip to chapter 11 and take a look at it and see if the math you did looks similar to what is done there.
Okay.
Okay. All right. Anyone else?
Is-
Yes, go ahead.
Yes, is it okay for us to use our own photos? Like in our presentation?
Yeah,
Okay,
absolutely.
just wanted to.
Have fun with it. I really want you guys to have fun with it. I want you to use a little bit of creativity and don't just get bogged down by this is a math final and I'm super nervous. I want you to have a little fun with it. That's why I always encourage you to choose a topic that you're really interested in because you're going to have more fun with it.
Would that, I know sometimes you'll take, like, if you really like the presentation, you'll take it and use it as an example in another class. Would that stop you from doing that though? Mine's about hiking and
I
it includes places I've taken my kids.
I
So
always
it'd probably be photos of my kids.
So everybody that I've used the presentations for, I've asked them their permission and I take their name off of it. And
Oh, okay.
if for example, you had one and you said, all of it's good, but that one picture that shows my son's face, can you take that one off? I will take that off and I'll find a random Google picture to put on there.
Okay. Thank you.
I always ask first.
Thank you.
Yeah. All right. I'm going to turn off the recording.